Mm.
We'll get started here in a second. Okay, I think we're going to go ahead and get started. Let me share my screen with you. Okay, today, well, I have on here that we're going to go ahead and whiteboard worksheet 1. I was looking at those last 3 questions, or question number 9, and it said something about elastic. So I think before we whiteboard those, I think it might make more sense to do the lab, and that way we could talk about what does it mean for an elastic collision or inelastic collision, that kind of stuff. So what I would like to do is whiteboard your graphical mathematical models for the lab, and I just want to kind of remind you what the lab was. So you were doing at least 6 different collisions. 2 of them had to be elastic. So for instance, you could have an elastic collision like this, or you could do something like maybe have them move in the same direction, elastic collision, something like that, or maybe have them move in the same direction, elastic collision, something like that, whatever. I'd like you to have 2 inelastic collision. That's somewhere in between, doesn't have to be 58%, whatever, somewhere in between inelastic collisions. So again, you could do whatever you want. You could change the mass. And then 2 perfectly inelastic collisions. Again, you could do whatever you want. You could change the mass or whatever. Okay, at least 2. So you have 6 collisions. And what you're looking at is the total momentum before the collision. Like for instance here, the total momentum would be, if you add both of those together, you get negative 1.15. And then the total momentum after the collision. So after they collide, you have to look at the total momentum again, figure out what it is. And so you're going to plot probably the final depends upon the initial. So final momentum versus the initial momentum of the system. And I just shared, excuse me, I just shared whiteboards with you. And all I want is for you to kind of sketch what your graphical model looks like. If you could label the axes, so this would be final momentum, and the units would be kilograms times meters per second. Rotate that, and you could do the same thing for the other axis too. Title it, please. It would be even nice if you could put point protectors. I mean, you could draw little circles on the line, right? You can even do little slope indicators with, just kind of drawing an X on it. And then if it had to be linearized, and then if you could also kind of write your mathematical model for that consensus, okay? So let me stop sharing, and I'm going to give you like maybe 5-6 minutes to put together your whiteboard. So let me go ahead and open up the breakout rooms for you. Elena, evidently Aiden isn't here this morning, so you don't have a partner. Is that okay? I could put you in a group, but I figure you're probably going to want to work on your own whiteboard.
I think, yeah, I can just do it alone.
Okay, all right. Okay.
Yeah. Okay.
Come on in, your magic. Come on, buddy.
Then independent variables, mass.
No, you wait. You can change those if you want to. It's
Exactly.
just
Doesn't that make
the
an
independent is the final movement. No, wait, hold on. No, it's initial is the thing. Wait. Yes.
Oh
Initial.
yeah, I think you're right. I think it's the initial, right? I mean, because you're kind of controlling the initial momentum and you're seeing what the end result is. So yeah, I agree. Yeah, the dependent would be final momentum.
Ooh.
So what kind of relationship did you guys get? Or are you
I
still
got
working on it?
perfect linear, like 1-for-1.
Huh. Okay. Cool. You guys okay?
Mhm.
What kind of relationship did you guys find? Or are you still working on it?
We
We
got
got
a
a direct.
direct.
Direct. Okay. Cool. You guys need more time?
No.
No. Okay.
Yeah.
Did you guys need more time?
No, I think we're okay.
Okay. Did you guys need more time?
Yeah.
Yeah, just a little bit.
A little bit. Okay. Couple minutes or?
Yeah.
Okay. Did you need more time?
No, everything is good.
Okay.
Don't care.
Did you guys need more time?
No, we're good.
No. Yep, we're good.
Okay.
It's so crazy.
Did you guys need more time or are you okay?
I think we have it.
okay.
Okay. Okay, so I'm going to share my screen with you and then we're gonna look at everybody's, I'm hoping we could look at all the whiteboards, okay? So share, okay. And, okay, this is Sydney and Gabe's and it looks like they had, it looks like they have a linear model, but their mathematical, or excuse me, a direct model, but their mathematical model over here looks like it has a y-intercept of 9.07. That's pretty big. You can't drop it off, right? Is that true?
We might be able to. I'll check in a second.
Maybe it's 9.07 times 10 to some number, maybe.
Mm, no, I got 9.07. Oh, it is to -5. I didn't see that.
Oh, okay. So yeah, that's probably pretty small. You
probably
probably
could.
drop that off.
Mhm.
Okay, so that one looks like it's direct model. Let's see. Back. Okay, Vlad and Jaden's. It looks like they have a direct model as well. Okay. Jack and Chaitanya's. I think it's on here. They have a direct model as well. Lena and Aiden's. Looks like it's a direct model as well. And we're all getting the same slope too. Looks like the slope is 1. And let's see, Wendy, Chloe, and Sophie. Looks like a direct model as well. Okay. And Brett, Nathan, and Luke's. Okay, looks like a direct model as well. Alex and Nathan's. Looks like a direct model. And I think we have one last group. And Aiden's and JJ's. And they have a direct model as well. So we have consensus here. It's a direct model. Okay, so let me go back. Actually, I could just pick any one of these. So we all agree on the math, on the graphical relationship. So make sure it kind of looks like this with the units, the title, the slope indicators, the point protectors. The title should be PF minus or PF versus PI. And the mathematical model is that PF equals PI. Okay, so I want to go back to what the lab kind of looked like. So if you remember before this, we said that impulse equals change in momentum. But now we're saying that there is no change in momentum. We're saying the initial momentum is the same as the final momentum. Well, that's when you're looking at both of these two combined. So I'm going to play this. I want you to just watch the red one, just the red one. Oops, wait a second. Let's do a more interesting one. Let's do elastic. Let's reset this. So just the red one. Okay, so did the red one have a change in momentum? So you have to unmute yourself. Did it have a change in momentum? Just the red one?
Yes.
Yeah, it did. So in other words, the red one had an impulse on it, okay? So the red one right there had an impulse on it. Let me ask you a question. Does the green one have a impulse on it? Does it have a change in momentum? Yeah, it does, right? So here's the question I have for you. How does the impulse on the red one compare to the impulse on the green one? Any ideas?
The same.
The same.
Well, almost the same. It's equal and opposite. Newton's third, the forces are in opposite direction. The time is the same. The time is perfectly the same, but the forces are equal and opposite. And so therefore, that's why the momentum initial for the system, if you're looking at the red and green combined, that's why the total momentum doesn't change for the two of them, because it's only an internal force. So I'm going to restart this again. There are no external forces. There was an internal force right here that caused a change in momentum. It caused a change in momentum on the red one to the left, and it caused a change in momentum on the green one to the right. That's an internal force. It's kind of like you sitting inside of a car pushing on the dashboard. It's not going to make it go any faster. Now, when you push on the dashboard, do you move backward? Yeah, you do. Does the car move forward slightly? Well, yeah, slightly, but not very much because the mass is so much bigger. But the truth is, you moving backward and you're still in the car, and the car moving forward a little bit, those two cancel one another out because you're still inside the car. Okay, so that's what's kind of going on here. So even though the red one does have an impulse, the green one has an impulse that's equal and opposite, so that the total momentum stays the same. In fact, from this lab, what we're learning is that momentum is conserved. It's kind of like energy, it's conserved. Well, it's actually a little bit tougher than energy, because with energy, you didn't have to worry about direction. With momentum, you have to worry about direction. So the initial momentum is equal to the final momentum. That means not only the mass times velocity, the mass times speed has to be the same, but the direction has to be the same too. So it's kind of interesting. So what I want to do next is I think I want to talk about some of these things. Hold on a second, sorry. I have to get back to my phone. There we are. So some of these questions I want to talk about, like 17 through 19. In fact, we just talked about number 17 a little bit. Clearly the momentum of any one car did change. The red one changed, okay? Therefore, it must experience an impulse. How does the impulse of that car compare to the impulse of the green car? This is where you guys unmute yourself and say.
Equal but opposite.
Yeah, there you go. So that's the answer for that one, equal and opposite. Okay, now I want to talk about number 18, because I gave you these weird definitions and I never explained them because I wanted you to kind of look at it a little bit. In fact, I'll come back here and do it. The first one is looking at perfectly inelastic. So let me reset this up. And right now I have it as elastic, but let's change it to perfectly inelastic. I want you to watch what happens when it's perfectly inelastic. Okay, and I could do it differently. It doesn't have to be like that. It could be like this. Perfectly inelastic. Or let's do one more. Let's say this one's moving that way. So for every one of those, what did you notice about perfectly inelastic? What happens?
They kind of stick to each other.
Right. And so whenever you see perfectly inelastic, I want you to think of like, you know, like Velcro or something where they get stuck together. So let's come back to that question. So think about the final velocity of them. So after the collision, think about their final velocity. How did they compare? Everybody, unmute yourself.
It was the same.
They're the same. That's right. That's the definition of perfectly inelastic collisions. They have the same final velocity because they're stuck together like Velcro. So now you know the answers for 17 and 18, okay? Now I want to talk about elastic collisions. So let me reset this. Here we go. All right. So let's see if I can make this velocity 0. Elastic. Okay. Now this one's kind of hard to, whoops. This one's kind of hard to see. And I might have to point it out to you. I don't know. We'll see. See if somebody can figure it out. There's something interesting about this one. So there's one possibility. They could be going like this. They could go like this. Okay, did anybody see anything that was interesting about this when it's an elastic collision? Kind of unmute yourself.
Does it like transfer like the most, I would guess, like momentum from one object to another?
Well, that's the interesting thing about this, that momentum's conserved no matter what type of collision it is, whether it's inelastic, perfectly inelastic, or elastic, momentum's always conserved. So there is a transfer of momentum that's going on. And you're right, there is a transfer of something, but it's more than momentum. And so I'm going to reset this. This time what I want you to do is, can you guys see my cursor? Right up here, it shows the kinetic energy. I want you to watch the kinetic energy, okay? So look what it is right now, okay? And I want you to watch what happens after the collision. What did you notice about the kinetic energy?
The same.
Yeah, now that kinetic energy is not the energy of the red, it's not the energy of the green, it's the energy of all of it, everything. So let me go back. Let's do this one where it's not moving. 0. And let's hit play. So look at the kinetic energy. Did you notice it did not change? did not change. Let me do one more. Watch the kinetic energy again. Okay, so for the elastic, it doesn't look like it changed. Let me go back to the perfectly inelastic, where they get stuck together like Velcro. Now watch the kinetic energy. Do you see that it changed? It's not the same. Okay, in other words, I don't know if you guys heard the click there, but I turned on the sound. The truth is, even when it's elastic, it makes a noise, but when it's perfectly inelastic, there's a lot more dissipative energy losses. When it's elastic, there's no energy losses. Let me do another perfectly inelastic. So let's say they're going like this. Watch the energy. This is perfectly inelastic, like Velcro. You see how it dropped? It changed, okay? So reset. And now I'm also going to do just regular inelastic, okay? So this means they won't get stuck together. So look at the energy. In fact, maybe I'll set this to 0. Play. So there's a little bit of bouncing, but notice how the kinetic energy went down, okay? Now let me do that same one again, but now I'm going to do it as elastic. So watch that energy again. Okay, now it's elastic. You see that? So there's something special that happens when it's elastic. So let me go back to that question again. When it's elastic, what's true about the final energy and the initial energy of the whole system?
They're equal.
They're equal. Okay, so this is really important. Elastic collisions are usually a little bit tougher because now there's two conditions. Momentum is always conserved unless there's an outside force like friction. Momentum's conserved. That's the one we just found. And if it's elastic, energy is conserved. Kinetic energy is conserved. I mean, of course, energy is always conserved, even for inelastic collisions, but it turns into dissipative. So I'm really talking kinetic energy, okay? Kinetic. Does that make sense? I misspoke there. It's kinetic energy is conserved, okay? That's the defining characteristic of elastic collisions. So we talked about perfectly inelastic. We talked about elastic collisions. I also want to talk about just simply inelastic collisions. So not perfectly inelastic, but just simply inelastic collisions. How would you define them? Okay, so let me review.
They,
Oh, so go ahead. Go
they
ahead.
still bounce off each other like elastic collisions, but they also lose energy.
There you go. Okay, that's exactly it. So they're not stuck together. There's no like Velcro. So if it's inelastic, they still kind of bounce off one another a little bit, okay? And their kinetic energy is not conserved. So you still have some dissipative energy losses. Okay, very good, nice. Okay, so then where are we at here? Takes care of those two. All right, what do I want to do here? Let's see, 920, do I want to just finish this? Yeah, you know what, let's just finish this lab up. Let's actually whiteboard this. So in order to solve these, we're only going to do 20 and 21 right now, is you have to use this new idea that PI equals PF. Now you have to realize that if you have more than one object, I would recommend kind of sketching a picture for these. So for instance, this one here, it says we have some train. So I'm going to have this train be blue and it's moving. Oh, come on, really? So we have this blue train car that's moving and it's colliding with another car that's at rest. So I'll have this one be red. So this is my before picture. So that's before the collision. I really recommend kind of drawing this out so you have to imagine the collision. Okay, then after picture, it says, what's the final velocity of the two-car system, assuming the collision is perfectly inelastic? Based on what we just talked about, what's true about perfectly inelastic collisions? How are they moving?
Same velocity.
That's right, they're stuck together. Okay, so let's see if I can recopy this picture. So the after picture looks like this. They're moving together like this. Oops, sorry. They might be moving faster, slower. I'll let you guys figure that out. So maybe my little lines here aren't drawn exactly right, but they're moving together. And this is my after picture. Oh, come on. Here we go. So that means here's my equation. This equation goes with my picture. So over here is the PI. Equals PF. Okay. You need to understand there's two things that might have PI. So we got the blue car and we have the red car. Now this one's kind of easy because what's the momentum of the red car before the collision?
0.
0, right. And then afterwards though, we do have two things that have momentum, both the red car and the blue car. Okay. So how about I give you 2 or 3 minutes to work on this problem. So I shared again this folder with you, and this is problem number 20. And in fact, why don't you go ahead and start doing 21 too, where please draw a picture and stuff. All right. So let me, oh, stop sharing. That's what I have to do. Stop sharing and open up the breakout rooms. Hey, Justin, you should get an invitation for a breakout room. Justin, can you hear me? Justin, can you hear me? Justin, can you hear me? Please respond. Okay, is somebody willing to share their whiteboard so we can see the answers you got for those two problems?
Yeah, I can do it.
Okay, sounds great.
So yeah, we just set it up. The mass of or the uh, initial momentums equals the final momentums, and this bit that we got right here, if the velocities are the same, you can just distribute it out, put it in front, and
Nice.
so it was pretty easy to solve from there.
Nice. I kind of made a mistake in this problem because I didn't say a direction like 3.5 meters per second to the east. Please understand that I made a mistake there, and so you would want to say the exact same direction, right? Because it was going to the east and or whatever direction it would continue going that way. So that was my mistake. All right, thanks very much. Appreciate it. Everybody give Gabe a hand. Nice, yay. Okay. Did you guys need some time to do the next one too, or can somebody present the next? So do you guys need a little bit more time then? Yes?
The
Yeah.
billiards table.
What's that?
The billiards table.
Yeah, the billiards ball one.
I have it done, but we can.
Okay, how about Jack? I'll have you share in about 5 minutes. I want to give everybody time to kind of work on it. Okay, so Jack, you want to share your screen with us? And so we're looking at 21 there, and there's the setup for it. Nice.
It's basically the same like thing over again, just with one of the balls now has like, because it perfectly transferred all the velocity to another ball.
Okay, so Jack, JJ, I have a question for you then. So we know momentum's conserved here because that's what you did. You used momentum conservation to solve it. If I asked you, is energy conserved here? Is kinetic energy conserved?
Yeah.
It is, right? And it's really easy to figure that out because they have the same mass and they also have the same speed. So therefore, JJ, what kind of collision is this?
Is this an elastic collision?
Yeah, this is elastic collision. So in fact, billiard balls are really good about having elastic collision. I mean, it's not perfect. There is some dissipative energy, but it's pretty close. Nice. Everybody give JJ a hand. Thank you. Yay. Nice. Yay. Okay, so what I would like you to work on really quickly here then, I'm going to give you a little bit of time, is number 22. Please don't get started on 23, 24 because it's a little bit tougher, but just 22. So why don't you go ahead and start working on that one now.
Are we just done with the Zoom or what's going on?
No, we're not done with Zoom.
Okay.
So you should have got an invitation. You didn't get an invitation?
No, I got kicked out.
Oh, wait a second. You got kicked out.
Like not kicked out, but it just ended for me. Yeah, same with Aiden. 'Cause he just texted me.
Okay, wait a second. All right, so who's talking? Is this Brett talking?
Yeah. Yeah.
Yeah.
Yeah.
I did.
You don't have an invitation? Okay, so
No, when I tried to come back from my breakout room,
okay.
it like said this might take a few moments and then just complete.
What did they?
Sorry, Aiden. I hit the wrong button. I was getting ready to put you in assign you to a room. So there, you should get it. You should get an invitation now, Aiden.
Yeah, I got it.
Okay,
Thank
cool.
you.
And Brett, I don't know why you're not. I'm going to move you to a room, Brett, and then I'll move you back, and we'll see
All
what
right.
happens.
Thanks.
Yep. Let's see, 5. Did you get an invitation now?
I'm not seeing one. Yeah, no, I didn't.
What the heck?
Oh, I can just join it by clicking breakout rooms. All right,
There
I'm
you
going.
go. You're in room 5.
All right.
Okay. Okay, so I think everybody's back now. Somebody want to share just this one problem, not the bottom one. Somebody want to share theirs, a different person? Titania, okay. All right. So walk us through, Titania, how you got that. You have to unmute yourself.
So we found the semi-trailer going at 5. We found the momentum of the semi-trailer, and the momentum of the VW bug is just 0. So the
Right.
initial momentum for like the total system would be 50,000. So the initial momentum would be equal to the final momentum, and we just divide by the total mass, and that's how we got the VF.
Right. And again, I made a mistake here. I probably should have said to the north or something. That means the final velocity would also be to the north. Awesome. Give Chaitanya a hand. Very good on reactions. Nice. Yay. And then Chaitanya, if you can hit stop share, I think it's like a red button. There you go. All right. So let me share mine with you because I want to talk about this last one. This is a two-parter. That's why I said 23 and 24. So this one's kind of hard. I don't think we're going to have time to whiteboard it, but I'm still going to want you to do it. So kind of like homework here, all right? So this is the picture, okay? So notice it says we have 2 skaters, one's 70 kilograms is on the right over here, and one's 48 kilograms on the left, okay? The skater on the right tosses a ball. So this one over here on the right is going to throw a ball this direction, right? To the 48 kilogram one, she's going to catch it, okay? And you're trying to figure out their velocities after all's said and done, okay? So this is how you solve the problem, okay? So I'm going to kind of circle this. The first part of the problem, you can't do everything at once. That's the biggest mistake that students make here. Okay, so don't try to do everything at once. The first part of the problem, you're only looking at the person on the right and the ball, and she's just sitting there. So I have a question for you. I'm hoping you can all unmute yourself. Before she throws the ball, before she throws it, what's the total system momentum when she's just holding the ball?
0.
It's 0, right? So on the left-hand side of the equation where it's PI equals PF, the PI is 0. The PF, you're going to have the ball going one direction. Oops, can't do this. All right, you're going to have the ball going one direction, and she's going to be moving the other direction, okay? And so the PF is going to be PF of the ball plus PF of the girl. Be careful because they're going in opposite directions. You got to make something positive, something negative, okay? It says that the ball is being thrown with a velocity of 5 meters per second there. So we know what the velocity of or the speed of the ball. You have to figure out if you're gonna make a positive or negative. Okay, and then you can calculate her velocity. Any questions about that? So that's like number 23. Okay, 24 then is her catching it over here. Okay, so before she catches it, she's not moving, she's just sitting there, she's getting ready to catch it. Before, so it's again, PI equals PF. Before she catches it, what's her momentum?
0.
It's 0. But before she catches it, the ball does have momentum because it's moving. It has its mass, it has this velocity here of 5 meters per second, okay? So before she catches it, the ball has momentum. After she catches it, so that's the collision part. After she catches it, what kind of collision would this be if she's holding on to the ball?
Inelastic.
Yeah, this is actually, it's not just inelastic.
Oh, perfectly inelastic.
It's perfectly inelastic because her and the ball are moving together. So they're moving together, okay? So they're stuck together. Any questions on that one? Because I don't want to take too much time. I've already been going like almost 50 minutes. This is a hard problem. All right, so really quickly, what do I want to do? Oh, so step 3 here where it says start this homework, don't worry about that because I didn't get as far as I wanted to. So don't worry about that. I'll change the calendar here in a second. Hopefully you have already worksheet 1 finished. We'll whiteboard that on Monday. I would like you to do for homework is finish up this lab response in those folders that I shared with you, and make sure everybody's contributing. Make sure your name's on those. And you've already shared it. You don't have to share it with me because I have it. I shared it with you, and I'd like you to turn that in by midnight. So that's your homework. Also, there's an attendance quiz here that I would like you to take. So the attendance quiz is kind of just over the stuff we found today in the lab, you know, what kind of model it was and that kind of stuff. And the code is 409-276-482. 409-276-482. Okay, so let me repeat what it is I want you to do. I want you to do that attendance quiz, which is just the models and stuff that we found from the lab, the information we found from the lab, and I would like you to turn in that lab by midnight, so don't worry about number 3 here. So I want to stop sharing. I do have to get a picture of you guys. Hey, I'd like to do something different for fun. I'm hoping that maybe you guys have pets or maybe a cat or something. Can you guys go grab a pet and bring it so we can kind of see it? You can hold it up and get a picture of you and your pet if you have a pet. There were some pretty good pictures earlier this morning. Oh, look at that cat. That's photogenic. That's nice. Hey, that's not a pet, Gabe.
The other one's too rowdy.
Oh, nice. Cool. Oh, look at all these. We have a lot of dog lovers. Oh, there's a cat. I have a cat too. I can't find mine. He's hiding. I grabbed him early this morning. He's like, what is going on here? Dogs like the attention though, so they love it. Okay, I'm gonna get a picture here. Is there anybody else grabbing their pet? Okay, so I'm gonna get a picture. So, oh, Alex is getting a pet maybe. No? Okay. So I'm gonna take a picture here. Count of 3. 1, 2, 3. Nice, thanks. I appreciate it. That was kind of fun. So I wish we had more time that you could introduce your pet to me, but I kind of went long today. So that's it for today. See you on Monday. Don't forget, get that lab turned in to me. Just all you have to do is complete it there in the folder, and I have it. All right. So have a nice weekend. See ya. Bye.
See you, Mr. Fessy.
Bye.